This presentation opens with Locard's exchange principle, the simple but powerful idea that every contact leaves a trace. Think of it as the foundation of trace forensics. Whenever two surfaces meet, microscopic materials transfer and can later be detected, analyzed, and connected back to people, places, or events using an integrated analytical framework of contact, trace recovery, and laboratory interpretation. Here we trace the evolution of forensic science after World War I, when advances in microscopy and analytical chemistry transformed intuitive observation into a systematic scientific doctrine. Locard's Lion Laboratory standardized collection and analysis protocols, shifting justice systems from confession-based prosecutions toward evidence-driven conclusions, and paving the way for broader European adoption of verifiable physical evidence in court. This slide illustrates the main mechanisms by which trace evidence moves. Fibers detach through friction, metal particles abrade and adhere under pressure, cosmetics smear and leave residues, and biological cells shed naturally. These predictable transfer behaviors guide investigators to likely locations, high contact surfaces, entry points, and victim interactions, and help select the right collection methods for successful laboratory comparison. Trace evidence is fragile, and its value depends on context. So this page highlights threats like weathering, UV exposure, cleaning attempts, and secondary transfers that can obscure provenance. Distinguishing primary contact from innocent background transfer is crucial, and careful timeline documentation and chain of custody handling are essential to preserve reliability and withstand courtroom scrutiny. Systematic collection protocols maximize recovery and preserve evidentiary value by matching technique to trace type. Tape lifting secures fibers and surface debris. Vacuuming concentrates dispersed residues from large areas or vehicles. And swabbing or scraping targets biologicals and gunshot residues on surfaces. Integrating these methods with rigorous documentation and sealing helps sustain the chain of custody and improve laboratory comparability. Two short case studies show how minute exchanges carry weight. Matched glass fragments on footwear linked a suspect to a broken window, while unique pollen grains on clothing tied someone to a remote meadow. Together, these examples demonstrate how probabilistic associations and careful laboratory analysis can reinforce investigative narratives and provide strong support for arrests and prosecution. Objective laboratory techniques strengthen trace interpretations by providing repeatable, documented comparisons. Stereo microscope exams allow side-by-side feature documentation. Polarized light reveals fiber morphology and common origin hypotheses, and SEM-EDS elemental profiling identifies metallic traces. Combining these methods produces robust physical data that support expert testimony while enabling peer review and transparent reporting. Advances in molecular methods let labs amplify tiny amounts of trace DNA, but low template profiles present interpretation challenges, such as drop-in contamination, allele dropout, and contributor mixtures. Probabilistic genotyping and likelihood ratio calculations help assign weight to these complex results, allowing analysts to quantify evidential support rather than rely on simplistic match statements. Maintaining trace evidence validity requires awareness of risks like confirmation bias, irrelevant associations, and overstating uniqueness. To prevent speculation, forensic practice emphasizes safeguards including blind examinations, well-curated population databases, and error rate studies. These measures promote objectivity, reliable conclusions, and ultimately safeguard justice by ensuring scientific results are reported with appropriate context and limitations. Finally, emerging detection technologies, portable spectrometers, real-time chemical imaging, and AI pattern matching promise faster and more sensitive trace detection. But they also demand rigorous validation, ethical oversight, and transparent reporting. Balancing innovation with standards and public accountability will be essential to integrate these tools responsibly and maintain trust in forensic science.